Hello everybody. Today we're going to be looking at systems of linear inequalities with some applications. So we've looked a little bit at systems over the past few lessons, but we were dealing with systems of equations. So we were looking for distinct points where those equations were intersecting for our solutions. Now if we're looking at linear inequalities, which is the focus for today, the only way we're going to be able to solve is by graphing, and you're going to see why in just a minute. Now I need to back up and make sure we remember how to graph a linear function. For instance, if we were graphing something like y equals 2x plus 1, hopefully remember that the 2 in front of the x represents our slope. So if our slope is 2 or 2 over 1, that means I can rise 2 and run 1 to get from one point to the next. And our y-intercept, b here, is 1, so that's where we begin our graph on the y-axis. So if I was going to sketch this out, and this is going to be really rough, let me just apologize in advance for that. This graph would start on the y-axis, we set at positive 1. And then because our slope is 2, I'm going to go up 2 and right 1 to make my next point. So if I go up 2 and right 1 and make my next point, then I can connect those 2 points to create that linear function. Now this point here, any point on that line, we connect to form that line because technically every point on that line represents a solution to that equation. So for example, the coordinates here are 0, 1. Or the coordinates here are at 1 and 3. If I was to plug 0, 1 into the function, or plug 1 and 3 into the function, so this x and this y, or this x and this y, or any point on that line, it's going to make that true statement. So, for example, if I plug in 0, 1, right? If I put in 1 for y and put in 0 for x, I get 1 equals 0 plus 1, and 1 does equal 1. That's a true statement. That means this is a solution to that equation. Or similarly, if I plug in 1 and 3. So 3 for y and 1 for x. Again, I get 3 equals 2 plus 1. So 3 equals 3. Again, a true statement means this is a solution to that equation. So every single point on the line, that's going to be true. If I plug every single point on that line into that equation, it is a solution to that equation. That's why that connection of points is the graph of that equation. Okay? So if we're graphing an equation, all the points on the line are solutions. Now, if I was to change my equal sign to, let's say, a greater than or equal to 2x plus 1, well, I still have the y equal to portion in there, which means that the points on my line are still going to be considered solutions. So I would graph this the same way, has the same slope, has the same y-intercept. All the points on the line equal to are still considered solutions, but now we have this extra piece, right? If we're greater than or equal to, that means that not only are the points on the line considered solutions, so we would still have this same graph here, but now all the points greater than that line, which are above that line, are also considered solutions. And to represent those solutions, we would shade the area above the line. Okay, now let me take that away. If I made this, let's say, a greater than without the equal to, well, then the points on the line are no longer representing solutions, which means I would have to graph a dotted line to say the points on the line are not solutions, but since we're still greater, that means only the points above are going to make this true. So I pick a point clearly above, like, let's say 0, 3. Right? 0, 3 is going to be in that area I shaded. That should be a solution to this inequality. So I put in 3 for y and 0 for x. What I end up with is 3 is greater than 1. Again, that's a true statement. That implies this is a solution to that inequality. And then if you switched it to, let's say, a less than, then that would be all the points below that line included in the solution region. So you have this whole set of solutions, right? It's like when you solve an equation, you get one solution like x equals 3, where you solve an inequality and you get a whole range of solutions, like everything greater than 3 is going to be in that solution set. Okay, so we have it's an infinite number of solutions, whether it's a line or an inequality here, but we have to shade to represent all the points that are above or below to capture that greater than or less than piece with the inequality. Okay, so if we're going to graph here, we graph our line, whether it's inequality or equation, we graph using the slope and y-intercept, so m and b, if it's in slope-intercept form, or we can find both intercepts and I'll show you this when it's in standard form. So for slope-intercept forms, when it's in y equals mx plus b form. Standard form is when it's got the x and y on the same side and then the constant on the other side. And I'll show you both, but hopefully it will look familiar. And then when we go to make our graph, so the plotting of points works the same as it does if it was an equation or an inequality. But we are going to use dotted lines when we have a greater than or less than without the equal to, and we're going to use a normal solid line like we would have for an equation if we have the greater than with the equal to and the less than with the equal to. So solid line if we still have the equal to. If we don't have the equal to, if it's just greater or less, then we're going to make a dotted line or a dashed line or a broken line or however you want to say that. And then we're going to shade above the line if it's greater than, equal to, or greater than. So the greater than piece tells us to shade all the points above because all the points above are going to be part of the solution set. And then we're going to shade below if we have a less than, equal to, or a less than. And the shaded region shows all the points that would make the inequality true. So again, that's going to be called the solution region. And if we're going to graph a system, that means more than one at the same time, which is really the goal, then the solution region, which is sometimes called the feasible region, is going to be where the shading overlaps. And you'll see that in just a couple of minutes, okay? Well, just to recap, how do we graph? So this one has a slope of 1, and it has a y-intercept of 1 as well. So we would start this graph by making a point on the y-axis at 1. And then if our slope is 1, we're going up 1 over 1 to make another point. And I can make as many of those as I want. Now, when we go to connect the points, we have to make sure we look at our symbol. This is a less than. It doesn't have the equal to, so I don't want to include any points on the line. So I'm going to graph with a dotted line to say, okay, this is like the cutoff for the solutions, but the points on this line are not considered solutions. Now, less than, this is a less than symbol here, is telling us to shade below. So all the points that are below this line, these are all the ones that we could plug in that would make that inequality true. And if you aren't sure, you could test it. I mean, don't do this every time, but pick something that's clearly in the solution region, like here, 5, negative 5. If I plug that in, if I put negative 5 in for y, and I put 5 in for x, I should get a statement that's true. And negative 5 is definitely less than 6. So that true statement tells me that is a point in the solution region. It's just a quick way for me to verify that I've shaded the right way. Okay? Get rid of that. So if you want to check, and if you're making notes for later, again, this less than is why I made a dotted, can't spell, made a dotted line, and it's why I shaded below. Okay, now if you look at number 2, we're trying to do the same thing, but our equation is in a different form. And so if you wanted to rearrange this to put it in y equals mx plus b form, you could, but I like to just find both intercepts here. If you're making a little table and you put a 0 in for x, you're going to easily be able to solve for y. If you put a 0 in for x, this term's going to go away, and you're just solving here. So if 3y has to be equal to 6 or greater than or equal to 6, that means y has to be greater than or equal to 2. And that's going to be where this line's going to cross the y-axis. And then if you do the reverse, if you put a 0 in for y, this term goes away, and you're left with 2x equal to 6, which means, or greater than or equal to 6, which x has to be greater than or equal to 3. And so this graph is going to cross the y-axis at 3. So plugging those zeros in, a quick way to see where your graph's going to cross the x and y-axis. So I can make a point on the y-axis at 2 and the x-axis at 3 and connect these points to make the line. Now this time I have the equal to, so when I connect them, I'm going to connect with a solid line. So all the points on the line are considered solutions. And then because it's greater than here, that means all the points above this line are also considered solutions. So because of this, it was a solid line, and I shaded above that solid line. Okay, and again, if you weren't sure, you pick a point clearly in your solution region and you plug it in. So if I picked something over here, like 9, 9, right, 2 times 9 plus 3 times 9 is absolutely going to be bigger than or equal to 6. So I can verify by picking something in the solution region, making sure it makes a true statement to verify that I have a solution, or have shaded the correct solution region. Okay? All right, now if we're looking at a system, we got to be a little more neat about the work. So I'm going to graph this first one. using a table. So if I go to find my intercepts, 0 for x makes this go away. So 2 divided by 2 tells me it's going to cross the y-axis at 1. So I can make that point. And then if I want to find the y-intercept, I'm going to put an x-intercept, put a 0 in for y. So if 0 goes in for y, I'm left with x and 2. So it's going to cross the x-axis at 2. So I can make that point. And then this equal to here tells me this is going to be a solid line. So I'm going to connect these with a solid line. And the less than tells me to shade below that solid line. Now, if you're doing this on your own paper, don't go too crazy with the shading because you're looking for not just the one solution region, but where two of them are going to overlap. So we go to graph the second one. The second one has a slope of -1, and since there's nothing out here, that means it's going to cross at the origin or at 0 on the y-axis. So I'm going to cross at 0, and then I'm going to go down 1 and right 1 to make another point. And I could do that. Oh, this graph is a little messy here. I gotta back up. I'm so sorry. These lines are really close, so I'm gonna have to be a little bit neater about my work here. So we said this first one was gonna cross 1 on the y and 2 on the x. And I'm just gonna make several more points here. So it's more accurate. You saw what was happening to my graph. Okay, let me use my line tool. And I missed. Let's not use the line tool. Okay, so something like this, and again, all the points below this line are included in that solution region. Okay, on the next one, so it was going to cross the y-axis at -1. Nope, just kidding. Going to cross the y-axis at 0. And the slope was -1. So down 1, right 1 to make another point. And I can keep going in both directions here. And this time I don't have the equal to, so I'm going to be connecting with a dotted line. And if you just wanted to make a bunch of points there, you could. Okay, so there's the blue one, there's the second one. And that's a greater than, so I should be shading above the blue line. Okay, so again, if you're doing this on your paper, it's going to look like a hot mess. But what you're looking for when you're looking for the system is the solutions that are going to make both inequalities true. That means you're looking for the area of the graph where both inequalities are shaded. And so you can see there's sort of like 4 different regions here. I'm going to highlight here just real quick. So this is a region in here. We got a region over here. We've got a region here, and then a region here, right? 4 different regions. Now in region 1, we don't have any shading at all. In region 2, only the red is shaded. In region 4, only the blue is shaded. But if you look at region 3, which is in between, we have blue and red shading. That's what we're looking for here. Where are both of them going to be shaded? So I'm going to darken in that solution region. And if you have a highlighter and you are brave, right? Where they're both shaded, where the solution regions overlap, is the solution region for our system. So I want to darken that in and make sure that it's clearly identifiable. That is my solution region. So in that area is where I have points that will make both of those inequalities true. And if you weren't sure, just like the others, you pick a point that's clearly in the solution region. Like maybe you pick, I don't know, 8, -5, right? That looks pretty clear to be in the solution region. 8, -5. If you plug that into both, it's going to make both of those true. Okay? So we're looking at graphing systems in order to maximize or minimize some objective function in a scenario. That's the goal, right? To be able to apply this process to a real-world problem. I'm going to put it out of context just so we can see the work involved, and then hopefully when we put the context back in, it'll make a little bit more sense. But we're going to be graphing a whole bunch of inequalities. We're going to graph our system. Okay, and the inequalities in our system, we could just call them inequalities, but in a word problem, they're going to represent some constraints to that word problem. And then we're going to find the coordinates of the vertices of the feasible region. So we're graphing our system, and we're looking for the solution region. Again, that's another name for our feasible region. And the vertices are going to be the corners of the area that's enclosed by that solution region. And when we plug those vertices into some objective function, we're going to be able to find a maximum or minimum value. And again, that will make a little more sense when we get to a real world problem, to an application problem, okay? So we have some objective function here. We're just going to ignore that for a minute. That objective function isn't going to be graphed. It's going to be something that we're trying to maximize or minimize. And what we're graphing are the constraints, the actual inequalities here. So I'm going to graph the first one in blue. So this one's going to cross the y-axis at -5. And careful because the scale is going by 2. So -5 is going to be there. And the slope is 3. So I'm going to go up 3 over 1, up 3 over 1, as many times as I need to try to make my line. And that's less than equal to, so I can connect those with a solid line. And because it is less than, I'm going to be shading below that solid line. Okay, so number 2, I'm going to graph in red. It's going to cross the y-axis at 7. So 2, 4, 6, 7 is going to be in here. And my slope is a -3, so down 3, right 1, down 3, right 1, as many times as I need to try to make a line there. And again, equal to, telling me to connect these points with a solid line. And greater than means shade above that solid line. So right now, this would be our solution region, this area here. That's where they're both overlapping. But we've got a third constraint, a third graph to make here. So I'm going to do this one in green, number 3. Number 3, we have x's that are less than 6. So this is going to be a vertical line at 6 on the x-axis, 2, 4, 6. Here, all those x's being less than or equal, so a solid line, solid vertical line here. And we want to be less, so we're going this way, which means this little tiny triangle in here is going to represent our solution region, okay? So that area I shaded in there, that is the solution region. And we have 3 vertices, 3 corners where this solution region is being enclosed. We've got a corner here, a corner here, and a corner here. So we need to know exactly where those corners are. And it's not, I mean, it might be kind of hard to read it on your graph, but the nice thing is, and I made a note to that here, Desmos is really great. So you should be able to graph by hand, but ultimately what we're looking for on the graph are these corners, and we can get those very easily from Desmos, more easily than we could by hand. So I'm going to go ahead and put this same system in Desmos, and you're going to see how wonderful it is for us here. So we have y less than or equal to 3x minus 5. We have y greater than or equal to a -3x plus 7. And then we have x less than or equal to 6. And we can see that we get that same sort of, well, I zoomed out quite a bit, that triangular shape that we had on our paper. And what we need are the corners of the solution region. So it's darkest in the middle there, that triangle, the same triangle we shaded on our paper. So I need to know the coordinates of these corners. So these 3 corners, goodness, let me try to get them all there. These 3 corners, okay, are the coordinates that we need. So I'm going to mark a couple of them down here. This point, okay, it's going to be at 6 and 13. And then we have one here at 6 and -11, which makes sense. They're both in that vertical line where x is equal to 6. And then the last one over here is at 2 and 1. Okay, so those 3 now, the whole triangle, go away calculator. Okay, so the whole triangle represents our solution region. All of the points in that solution region are going to make all 3 of those inequalities true. But what's going to happen is, if we have some objective function like we do in this situation, the vertices that we highlighted, the 6, 13, 6, 11, and 2, 1, those points are going to be where we have a maximum or minimum for that objective function. And you could probably tell which one's going to be the max and the min just by looking at the picture. But what we're going to do is plug in each of these x's and y's into that objective function. So let's call this one number 1, let's call this 2 and 3, just for organizational purposes. If I take number 1 and plug into my objective function, f equals -8 times for number 1, x is 6, plus 5 times for number 1, y was equal to 13. We end up here with -48 and a positive, 65. So f is equal to, subtract 2l upside down here. That's going to be, 17? Positive 17? Okay. Number 2, if I plug in this x and a y, we have -8 times x is 6, plus 5 times y is a -11. So f is equal to -48 and -55, which gives us a -103. And then the last one, f is going to be equal to -8 times x is 2, plus 5 times y is 1, which gives us -16 and 5. And -16 and 5 makes a -11. Okay, since this is the lowest value produced, this is the minimum value, then we would say that this this situation has a minimum value of -103, and that is produced by the coordinates 6 and -11. And then this is where the maximum value is produced. So this has a max value of 17, and is produced by the coordinates 6 and 13, okay? Now, out of context, it seems like, what the heck are we doing? But you're going to see how, put into a context, we want to be able to find a max or a min in a situation, okay? So let's look at our context here, which when we apply this process of maximizing or minimizing some objective function with constraints, we apply that to a real-world situation. We call it linear programming. So linear programming is actually pretty useful. Now this is a basic example that you're going to see here and on your practice, but it is a useful thing, okay? So let's say, for our situation, Evelyn and Elaine are customizing cell phone cases at their kiosk in the mall. They have enough supplies to customize up to 30 large cases and 80 small cases, and they know that they'll be able to sell at least 10 large cases and 60 small cases. However, they won't have enough time to customize more than 100 cases total. Now, if they profit $6 for every large case and $4 for every small case, what is their maximum profit, okay? So first we want to figure out our objective function. The objective function is what we're trying to either maximize or minimize, okay? So what are we trying to maximize in this case or minimize? Either one is going to give us our objective function. So in this case, we're trying to maximize profit, so our objective function is going to be for profit, okay? Now, what are we going to profit off? Well, it says we're going to be profiting $6 for every large case and $4 for every small case. But we don't know how many of each of those we're making. So let's call large cases X, and let's call small cases Y's, all right? So our profit is going to be $6 for every large case, plus it's going to be $4 for every small case. Okay, hopefully that makes sense. All right, so that is our objective function. We're trying to maximize profits. So I called P is for profit here. Okay, we're trying to maximize profit by selling large cases at $6 a pop and small cases at $4 per pop, okay? Now the constraints, they're going to take us back into our situation here. It says that they have enough supplies to sell up to 30 large and 80 small cases. That means the number of large cases, which we said was X, can be less than or equal to 30, right? They can make 30 or less large cases. And then 80 small ones, that means the number of smalls, Y's, has to be less than or equal to 80, right? They can make 80 small ones or less. And then it says that they're going to be able to sell they can sell at least 10 large and 60 small. So the number of larges is at least 10. They're going to sell at least, means greater than or equal to 10 larges, and at least, so greater than or equal to 60 smalls. Okay? Now, they won't be able to have enough time to go more than 100. They won't have enough time to customize more than 100 cases. That means the number of smalls and larges all together has to be less than or equal to 100. They can make 100 or less cases total. Now, it doesn't say anything in this situation about it, but notice in the picture that we're restricted to the first quadrant. The x's and y's can't be anything negative. We're dealing with small cases, large cases, phone cases, right? Since they can't be negative, those are technically constraints that we don't have to list them, but technically they're in there, right? That the number of x's has to be greater than or equal to 0, and the number of y's has to be greater than or equal to 0. We have to be dealing with things that are positive here, okay? So those are our constraints based on the situation. Now what we're going to do is we're going to graph all of them, and then we're going to try to figure out from our solution region where we get our maximum or minimum profit. So luckily these aren't too bad to graph, right? The x being less than or equal to 30, that's a vertical line at 30. So vertical line at 30 is going to be here, and less than that, so this way of that. I don't want to go too crazy with my shading. It's going to turn into a big mess. And then x's have to be greater than or equal to 10. So there's another vertical line at 10. And greater than or equal to 10. So we're in between that, right? There's our large cases. We're going to sell at least 10, and we can't make more than 30. So we're between 10 and 30 for the large. And then the small, those are our horizontal lines at 60 and 80. So we're going to be between 60 and 80. So 60, horizontal line there. Let me use my line tool, make this nice. 60 there, and we got to be more than that, so that's going to be up here. Okay, and then less than 80. So here, and less than that. Okay, so far we're in this square, and then we have the last one. Get rid of my arrows here because I already know where I'm at. Okay, I'm in that square. In between all four of those would be this area in here right now. But I have one more constraint. X's and y's together have to be less than or equal to 80. So if I was to make a table on this, let me do this in the same color. If I was to make find the y-intercepts, right, on this pink one, if I put a 0 for x, right, then y has to be 100. If I put a 0 for y, then x has to be 100. So I know that this last one's going to cross at 100 and 100. This should cut right through that. Let's see if I can get this. Yay. Okay. So that means, and we're less than that line, that means we're below that line. That means our solution region is going to be this area in here. Between those verticals and horizontals and underneath that pink one. So this is our solution region, and we're going to be able to maximize or minimize. I don't know why I would want to minimize profit, but whatever max or min is going to create is going to happen at one of the corners of this solution region. So let me label these. I'm going to call this 1, 2. Oh, my line tool is still on. Sorry. Call this 1. Or maybe not numbers. Let's use letters. Let me call this one A, this one B, C, D, and E. Okay? So the coordinates for A, what are the coordinates for A? A is at right here. Now, I did my graph pretty accurately, but I know that this line right here, this was where, this is the line for y equals 80. This was for y equals 60. This was for x equals 30. And this is for x equals 10. So I know at A that y has to equal 80. And like y has to equal 80. Right? And I'm looking for where it intersects the pink one. So if I think about this equation right here, right, if I know that the y value is 80, what does the x value have to be to make the 100? Well, it's got to be 20. And it looks like that because I made my graph pretty accurate. Although if you weren't sure, you could put this in Desmos like we did on the last one, and it would tell you exactly where all those coordinates are. But this isn't too hard to see that the 20 is the x value there. Okay, B, the same kind of thing is happening. B, I know, is hitting an x value of 30, and then the pink line. So if I put 30 in here for x, that means y has to be 70. For C, C is where x is 30 and y is 60. And then D, we have x is 10 and y is 10 as well. Not 10, no, I'm getting backwards, my bad. X is 10 and y is 60. And then E is where x is 10 and y is 80. Okay, now you could do the same thing we did on the last one on the front there. If you put all of those constraints in Desmos and tap on all those points, it would show you the same information. Okay, it gets a little messy because you're putting a lot of stuff into one picture, but it'll show it to you. Now, one of these coordinates is going to produce some maximum, and another one would produce some minimum value when we plug them into, remember, our objective function, what we're trying to maximize. So that's going to be the goal here, to maximize the profit. So I got to plug all these points in to the objective function. So the objective function said that the profit was going to be $6 per large plus $4 per small, right? So if I plug in A, for A would be 6 times 20 and 4 times 80. So that would be 120 and 320, which would be $440. So if they made 20 large cases and 80 small cases, their profit's going to be $440. Okay, if I plug in B, profit's going to be 6 times 30 plus 4 times 70. So that's 180 and 280, which is 460. So let's see, make sure I'm mathing this right. 120, 320 is 440, 180, 280, 340. Okay, so if they made 30 large cases and 70 small cases, their profit's $460. So far that's the winner, right? C, profit would be 6 times 30. Now, I probably wouldn't plug this one in. We have the same number of large cases, but 10 fewer small. It's clearly going to be less money, but just so you can see, this is 180 and 240, which makes $420. And then I'm running out of space, so D, profit's going to be less again, 6 times 10 and 4 times 60, which is, let's see, 60 and 240 is $300. And then E, profit's going to be 6 times 10 and 4 times 80. So 60 and 320, which would be $380. Okay, so the lowest profit that they're going to make in this scenario is going to be $300, and that's when they sell 10 large and 60 small cases. And the maximum profit happens at point B, when they sell 30 large and 70 small. So we're going to say here, to answer this question, that the max profit is $460 for 30 large and 70 small cases, right? This one right here. Okay, not so bad. I think the hardest part of all this is maybe, getting all this situation, making sure you understand what you're maximizing or minimizing, so creating your objective function and recognizing that the objective function does not go on the graph. It's just what we use after we make the graph. Getting all those constraints in there, right? Creating your objective function and writing the inequalities is the hard part. You should be able to graph by hand, but ultimately if you wanted to do all of this, the work that I did in Part C in Desmos, totally fine. And then once you have the vertices, those go into the objective function to find either your max or your min. Okay, so practice will be uploaded.